Thank you, Karen, and thanks again for the invitation. It's always a pleasure coming and meeting with people and sharing and learning from each other here. So today I'm going to talk about machine learning for networking. I'm going to structure today in the following way. First, I'll give some background. For instance, what are some of the problems we need to solve where we can apply machine learning to? Also, how is machine learning for networking different than its application in other areas? For example, detecting objects and images and so forth. Then I'm going to look at 4 different examples of how we apply machine learning. In the first one, I'm going to talk about intent-based networking, which is a new way of designing networks and operating them. And it's basically an architecture in which it's very easy to add machine learning on top. So I'll describe to you what this architecture is, and I'll show you some examples of how we apply machine learning on top. And then we'll look at 3 specific cases of machine learning for networking. First of all, identifying what's on the network, then identifying malware and encrypted traffic, and finally talk about coordinating machine learning across edge and cloud. Okay, first of all, what are the challenges people face? Here I describe 3 challenges as 3 different columns, and on the top you see the challenge, and on the bottom you see how machine learning can help. The first challenge is what we refer to here as a digital disruption. Basically, there's a huge number of devices coming online continuously. Estimates say that there are about 1 million new devices coming online every hour throughout the world. Okay? You don't know what these devices are. TVs, IoT devices, toasters, so forth. Machine learning can help you identify what these devices are and how the network should treat them, how the network should, for instance, protect them, and so forth. Second key issue is complexity. Studies have shown that people spend about $60 billion per year in terms of operating their network. Okay? That's a huge amount of money. Why do they spend so much money? Largely because most of the operations are done manually. And some other results or implications of them being done manually is that it's very slow to make changes in the network, and that there can also be errors in the changes because, as we type, we make mistakes. Humans make mistakes. So machine learning here can help by doing intelligent automation as well as generating insights at scale. The third key area, of course, is security. As you know, as we bring more and more IoT devices, for example, on the network, the attack surface is increasing. The attackers also are getting more and more sophisticated. They have deep pockets, sometimes government funded and so forth. And this leads to much more sophisticated attacks. Machine learning here is very valuable to give you faster threat detection and remediation of those threats. Okay, now let's look at how machine learning is different for networking than it is for some other application areas, such as detecting objects and images. And I'll just talk about 3 key attributes here. The first is that with networking, you have a huge amount of data, and it comes very fast. And it's a very diverse amount of data, different types of data. And often what you have to do is you have to fuse these different types of data together to help solve the problem you have. Let me go into this a little bit more detail. Here's an example of some of the different types of data you may have. And the availability to the data really depends on what use case you're trying to solve. First of all, who is talking to who? IP address, MAC address, user ID, device ID, so forth. Packet flow information. What application is there? Source and destination address, domain queries, so forth. What ciphers are using? Security info. For instance, there are a variety of threats out there. Fortunately, we have a lot of signatures of all the threats we have seen before, and we can use that to help identify threats and then stop them. Also, for a device on the network, know what its behavior is, what its typical behavior is, so you can tell if it's behaving abnormally. For example, it's malfunctioning or maybe compromised. And then a variety of application layer info, from multimedia to Google searches to location info and more. So once again, there's a very diverse range of data which may become available, and the availability depends on what use case you're trying to solve. Let me look at this other 2 attributes now. So every network is different. And I mean more than just topology. The figure suggests topology, but it's much more than that. So for instance, within 10 kilometers of this location, you have dormitories, you have hospitals, you have manufacturing plants, you have small businesses, libraries, so forth. Each of these places has a different network, okay? Have different sorts of devices on the network, IoT devices, other things. You also change what devices you have on the network. You change how you use those devices. When you update a browser, the network behavior changes. There are all kinds of things that are changing. So every network is different, and they also vary with time. The third key area is the content is encrypted. We're going more and more to end-to-end encryption. This is really good. It's really good for your security. It's really good for your privacy. The bad thing, though, is that bad guys could actually use these encrypted flows to hide malware and to get it into the system. So encryption is both good for us, but also leads to additional problems. And I'll talk more about that shortly. Since I come from Cisco, let me briefly mention Cisco's approach here. So, of course, we try to make the best of breed products, okay? And these, for instance, are the Catalyst 9K switch, which we believe is the best switch in the world, and the wireless AP 4800, which is the best wireless AP in the world. But more important than that, we try to bring those products together in integrated architectures. We call these software-defined architectures in a campus, branch, in the WAN, in the data center. And then on top of those integrated architecture, they're powered by intelligence, which basically means you use analytics and machine learning to help improve the reliability, the performance, the security, and so forth. What I want to do next is talk a little bit about integrated architectures, especially intent-based networking, so you can understand how we can apply machine learning on top of these architectures. Okay? So example one is intent-based networking. So the term intent-based networking, this is an industry term describing a technology trend and a market trend. This here is my conceptual view of how intent-based networking works. I like this view because I think that whenever I share this with somebody who has electrical engineering or computer science background, within 5 minutes they understand this and they understand basically how things work. Okay? So let me explain what happens. Oh, one other thing I should mention, intent-based networking, it's kind of the modern architecture for networking, and this is what everybody's moving to in terms of how they design their networks and how they operate them. Okay? So if we look at this, at the very bottom, here we have the physical and virtual infrastructure. This is where you have switches, routers, wireless APs, and so forth. On the top, you have a user over here, which has an intent. That is something they're trying to do. And then there are these three key building blocks: translation, activation, and assurance. So what happens here is that when a user wants to do something, they express that. For instance, I want to set up a telepresence session to talk with Karen. Okay? That intent gets translated into some network policies and security policies, which then are activated on the network. Okay? And they're automatically activated. So that's part one. Well, you don't just want to activate these things in the network. You also want to know, is the network doing what is intended? Okay, that's a very natural thing, right? And that's the goal of assurance over here. The goal of assurance is to look at the network data and its behavior and to determine, is the network behaving as intended? If yes, awesome. If no, why not? What's the problem? What's the root cause? And what can I do to fix it? And that feedback then is provided to the user, and the user can see this feedback. And if they'd like a fix, they can say, yes, please activate this fix. And then that gets applied in the network. And then you once again check to see if it works. This feedback loop here is really, really important. And this is one of the big changes that we have with intent-based networking. Okay? So I talked about intent. Let me give you an idea, some examples of possible intents. So what you see here is the 4 columns of 4 example different intents. And I show the intent over here, and then I show how it's mapped into some network policies and security policies here with the execution. Let's look at this middle one, because it's one of the simplest ones. I have scheduled a telemedicine session at 10 a.m. Okay? That's a very simple intent. It's something that a human understands really easily, right? Now that gets mapped into, on the bottom here, it gets mapped into, I want to create an HD video connection. I want to prioritize the traffic end-to-end via QoS. I want to validate the performance is what it should be with the network bandwidth, with the required bandwidth and low latency and so forth. I want to ensure everything, the communication safe via encryption. And at the end, I want to tear all that down. Okay? So you can see this relatively simple intent gets mapped to a large number of network policies and security policies. And in addition, we want to map it to the best practices for what these network and security policies should be. And that's the goal of the translation part, to figure out what this mapping should be. For those of you who would like to learn more about intent-based networking and how it compares versus traditional networking, we have this white paper that's available. You can just search for this on the web, and you can find very detailed comparisons of traditional networks versus intent-based networks. Okay. Now, how does machine learning help with intent-based networking? Well, if we look at it, it helps in all three of these basic building blocks. First of all, when we take this intent up here and we need to do the translation, it first needs to have natural language understanding to understand what is the human trying, what are they asking for, what is their intention, and then to make the appropriate mapping. Let's jump to look at this assurance now. What the assurance does is it looks at how the network is operating. It looks at the network data, the network behavior, and it tries to check, is it behaving the way it should? That's a lot of pattern recognition, classification, okay, and various other things there to figure out whether or not there's a problem, what the problem is, what the root cause is. And then it makes the recommended change to the user, who can then say, yes, please turn that on, and then it gets turned on. And then with this feedback loop, you can confirm whether or not it's working, and so forth. Okay? So machine learning actually comes into play in all these steps. Something I want to stress is that because of this feedback loop here, what happens is this feedback loop actually amplifies the value of machine learning. Because after you make a change, you can see whether or not it works, and then you can make additional changes very quickly. This feedback loop also is the major difference between intent-based networking and software-defined networking. Software-defined networking was basically this side, and nowadays we've added up this, so we made it a closed-loop system, which is very valuable. Okay, let's now look a little bit more at assurance. And let's look at a use case of assurance. Let's try to assure network performance. For instance, we all have applications that we hope run really well, right? That's an example of network performance. For an application to work really well, we need the data from the application, from this mobile device, to, for example, go over this wireless link to this, over a wired link here to a local WLC, over the WAN, to a data center, to a server that has an application, that has the application for this, and then to come back. And we need that all go with very low latency and so forth. So the reason this problem is complex, as you can guess, is that it's an end-to-end problem, and there are many different places in between where you can have an issue. So all of the different pop-ups you see here are example locations where you can have a problem. The goal of assurance is to figure out, is there a problem? If so, where is the problem? What is the problem? What is the root cause? And then how can I fix it? Okay? That's what assurance tries to solve. So let's look at how we make assurance. And here I'll talk about what we build, because this is a concrete example. So first of all, we take all kinds of different data to get an appropriate understanding of the context to figure out what the problem is. And as you can see here, there's a variety of different data we bring together. Then we do various sorts of complex event processing, like correlation across the various data streams, to try to figure out to get insights in terms of what the issues are. And once we figure out the issues and the root cause, then what the fix should be, so we can guide the user to remediate or to fix the problem. Okay? So these are the steps that occur for machine learning. And for assurance, and as you can tell, there's machine learning everywhere here. Let's look at one other thing I want to mention is this notion of assurance. It's been around for many years, but only recently have we been able to deploy it in any meaningful way. By meaningful way, I mean across wired and wireless networks, across the WAN, and so forth. So you can really get an end-to-end picture of what's happening, and you can identify a problem end-to-end and then solve it. And there's a huge number of opportunities here to apply machine learning and all kinds of algorithmic advances to help improve assurance. Let me mention one example here of how our assurance helped one customer, another university, which is nearby here. How many of you have ever had Wi-Fi onboarding problems? Probably everybody here has had a Wi-Fi onboarding problem, right? You have trouble getting on the network, or if you get on the network, you're not quite sure if you're on or not. You know, we've all had to deal with that, right? And you know it's very hard to diagnose what the problem is. What they had here at this university is that some of the students were sometimes having problems getting on the wireless network. As you can guess, that's a hard problem to decipher, right? What happened is, luckily, they had assurance, and they turned it on, and they examined it. And they quickly found out that there was actually a subset of students who had problems getting on a subset of the wireless APs. And it turned out those wireless APs were connected to a single wireless controller, which, by the way, was updated last night. But the software update was correct, and the certificate was correct, but it was out of date relative to the client certificate. Aha, that's where the problem was. So why did I mention this? I mentioned these various steps because often there are many steps between the observed problem and where the root cause is. And even if somebody who's an expert at networking or an expert in whatever their field could take hours or days going through this to try to track down the problem. Here, because we've automated these algorithms, they're able within 5 minutes to see what the problem is, the solution, and then to be able to solve it. Okay? So assurance is something that can be really, really useful. And there are lots of opportunities for machine learning here. Now let's look at example number 2, identifying what's on the network. Now, by this I mean we want to identify what devices on the network, what users on the network, what applications on the network. Intuitively, you can think the usefulness here is once you know what's on the network, you can decide how the network should treat these devices or users or so forth. As an example, we may want to have separate environments for the production servers from the development servers. So if a development server crashes, it doesn't bring down your production environment where you're providing web services to people outside. You may want to separate your HR databases from non-HR employees to preserve the privacy of this confidential information. You want to keep medical devices separate from the guest users in a hospital, so they can't accidentally interact with a medical device. And you want to improve quality of service for telepresence or AR, VR users, so forth. These are just some examples. Let me mention one other motivating example on the bottom here. What do these 3 companies have in common? And those are dollar figures next to them. Anybody have an idea? I'll give you a hint. It all took about 4 minutes, at least for some of them, to achieve those dollar amounts of damage, basically. That was the result of a cyber attack. It was the NotPetya cyber attack. It happened in June 2017, so a little over a year and a half ago. Wired has a really detailed and it's a very interesting article. It's a very scary article published last August, and I highly recommend you, if you're interested in this area, to read this article because you'll understand what happens. Let me summarize here. What happened is somebody wanted to attack the government of the Ukraine, and what happens is there's a small business there that was making tax software for the Ukraine, similar to TurboTax we have in the US. They hid some malware in that software, and then they basically turned it on and it affected a large part of the Ukraine. In addition, every international company that does business in the Ukraine, guess what? They have to do tax forms in Ukraine, so they have the same software. They may have only had it on one computer in their entire business, but the malware jumped quickly from that single computer to all the computers in the building, in the country, and then across the world. So very quickly, a lot of multinational companies had huge amounts of computers which were wiped by this malware. Now, the reason, one of the ways that the impact could have been reduced was if there was network segmentation applied. And even the Wired article describes that. Because if network segmentation was applied, you would limit the spread of the malware only to the area that that computer was allowed to communicate. Okay? For example, some of our customers had network segmentation applied. And for instance, one hospital only had 4 computers impacted by the virus. Okay? And that's because those computers were separated from the others. So clearly, network segmentation is good to limit the effect of these cyber attacks. Now, to do network segmentation, you actually need to know what's on the network. With that knowledge, you can know how to segment the network to do the right thing. Okay? Let's look at some examples of how we identify what device is on the network. I like this paper because it's about 2.5 years old by an academic group in Australia, and they looked at IoT devices in smart homes and enterprises. And they examined about 25 different devices, as you can see here by the various columns. These include things like Amazon Echoes and cameras like drop cams and various switchers and triggers like motion sensors, air quality sensors, blood pressure meters, light bulbs, internet-connected light bulbs, electronics like printers, and even non-IoT devices like laptops and smartphones. And so what they also did is they looked at about a dozen different network activity measures, okay? And then for each one of these measures, they clustered the intensity of the metric in 5 classes, from 1 to 5, and they used different colors to identify the 5 classes. Now what happens then is each column here, the colors in a column describe the fingerprint for that device. And as you look across all the columns, you see different color patterns. That is different fingerprints. And that's how we're able to basically accurately classify these different IoT devices. Does that make sense? In this example, they only had 25 different types of devices. So they're able to achieve a 95% accurate classification. In cases when you have more devices, it gets harder. But the same concept applies. So the approach here is that, first of all, we want to identify the devices on the network. And then we want to figure out the associated action we should take for those devices. So identify what device is on the network. Once we know the devices, the intent-based networking can then, for instance, separate the devices into different virtual networks, different network segments. And then we can do behavioral analytics. We can look at the behavior of each device and see, is it behaving the way it should? Or is it behaving in an anomalous way? If it's behaving in an anomalous way, that may suggest that it's either malfunctioning or it's been compromised. Okay? So topic 1 here and topic 3, both of those are classic machine learning problems, right? And there's a lot of machine learning being done here. Now you may ask, actually, where does the data come from to do this? That's very interesting because it comes from different places. For instance, some of the data is customized. For example, there are certain companies who their entire purpose of the company is to analyze medical devices and make databases of all the different medical devices, how to identify them and what their typical behavior should be, and what are signs of them malfunctioning. And then they sell those devices. They sell those databases. There's also crowdsourced databases where people throughout the world share information to make a global database. And in things like identifying threats, for instance, Cisco has a very huge database which we compose of threats. And I'm going to talk a little bit more about this because it's also useful for my third example. So Cisco Talos is a part of Cisco, and it has about 250 researchers working on threat intelligence. And we basically look at all the threats throughout the world, analyze them, classify them, so forth. As you can see here from the numbers, there's a huge number of threats that we identify and we put in our database. We also share this info with other security vendors and with governments and so forth to try to help protect society from all the attacks. Turns out Cisco is the #1 security vendor in the world based on revenue. So we're kind of bigger. We're bigger than most of the others. But you can see the number of blocked attacks we do per second. So these are actually attacks, and this is email that has malware in it and has spam. But it's about 2.5 million threats blocked per second globally. To put that in comparison, in terms of searches, for instance, Google searches, about 40,000 searches a second. So obviously, this number is much bigger. The reason this is so much bigger than, for example, searches is because searches are human-entered, done by humans. Attacks are automated. And that's why you have to have really good infrastructure to stop these attacks, because they're massive scale automated. OK. Now let me talk about example number 3. How can we identify malware in encrypted traffic? Now, the situation is the following. As I mentioned at the beginning, we're using more end-to-end encryption. I hope all of you are using end-to-end encryption for sharing your credit card information and other things. That's really valuable for your security, your privacy, and so forth. The problem, though, now is that what happens when there's malware? Because in the olden days, before we had encryption, before we did end-to-end encryption, the way you check for malware is you look at the packet flows, you'd have a signature of the malware, you look for that signature. If you see it in the packet flow, you stop the packet flow. Okay? But now the packet flow is encrypted, you can't do that anymore. The conventional approach is something called a trusted man in the middle. What that means is there's a box in the middle, it's a proxy, you give it the keys, it decrypts the content, then searches for the malware, then re-encrypts the content. Okay? As you can guess, this is very bad, because first of all, you have to give them the keys, so there's another potential security breach there. Then it breaks the privacy, and then it's very computationally intensive because you have all the decrypts and re-encrypts and so forth. So this is not a good solution. That motivated Dave McGrew, who's a Cisco fellow, and Blake Anderson about 5 years ago to look at the problem of can we identify malware in encrypted traffic without requiring decryption of the traffic, right? And it turns out that we can actually make a very elegant solution of this problem based on machine learning. And now what I want to do is briefly talk about that. So once again, the problem is, can we identify malware in encrypted traffic without requiring decryption? Turns out this is a very nice supervised machine learning problem, because we have large amounts of known traffic, benign traffic, let's say good traffic, and large amounts of malware traffic from Talos, which I just described to you a couple slides ago. So you have large amounts of both. From that, we try to extract the observable features in the data, and then try to identify which features are the best for discriminating between malware and benign traffic. Okay? And by doing that, they're able to create a detector which had an accuracy greater than 99%, okay, for detecting malware in encrypted flows. More details are in this article, which was on AI for Security conference. Let me talk about this in a little bit more detail. So let's look at some of the data features they looked at. So here's malware and benign traffic again. First of all, we look at the IP address. Is it, is it a prevalent address, a well-known address, or is it something on the watch list? If it's on IP watch list, obviously you should be worried. The domain, is it something like Cisco.com or Yahoo or Google.com? If so, it's probably okay. If it looks like that, once again, you should be worried. And then is the fingerprint for the transport layer security and the certificate, are they typical or are they unusual? Usually the bad guys, for various reasons, use unusual fingerprints. And that's something else that suggests that that may be malware. And in addition, it's the SPLT, the sequence of packet lengths and times, because by looking at the packet sizes and the interarrival times of them, going both ways between the source and destination, that also helps you predict what's happening. Let's look at this in a little bit more detail. So it turns out in an encrypted flow, before it actually becomes encrypted, the first packet is actually unencrypted, and there's a lot of useful information in the headers of that first packet. And this unencrypted information is very useful, once again, to help identify, is this malware or is this good traffic? And then we have the sequence of packet lengths and times. And let me describe this diagram a little bit. On the left, you have the source. On the right, the destination. This line here is the time axis. And whenever you see a line going upward, that shows a packet from the source to the destination, and its length is the size of the packet. Whenever you see a line going downward, that's a packet from the destination to the source, and once again, it shows the size of the packet. What you also see here is you see a number of packets and a number of lines in red, which show that they're unencrypted, and then a bunch of lines in black. Black means they're encrypted, they're hidden for us. That's why we color them black. Initially, there's a self-signed certificate. Then this big rectangle is basically a sequence of packets, all of the maximum size. It turns out that's data exfiltration. Somebody's stealing data. And there's a command and control message at the end. Okay? Now, if you look at this a little bit more, if you look at this packet pattern between a source and destination, for a Google search on this side and for malware on that side, they look very different. For example, here for the Google search, you see the source. You see some initial unencrypted packets. You see the initial page load. Then over here, you see that, for instance, I'm trying to refine my search, and there's some chatter back and forth as it tries to predict what I'm going to type. And then it's a new page refresh. So this is what a typical Google search looks like from a packet point of view. And malware looks very different on the outside. Okay? So why is this approach successful? This approach is successful, perhaps surprisingly, because some of the relevant features you need are actually sent unencrypted initially. And once you find that data and use it, it's very helpful for identifying malware versus encrypted traffic. You put that together with the communication pattern for the packets between the source and destination, and that provides a huge amount of information. By the way, here's some additional work by the authors. At the bottom also is a database of TLS fingerprints that they're making publicly available on GitHub, which you can use. And it's also part of the Joy software package, which is an open source software package they wrote that helps you capture and analyze various features from packet traces. Okay, now I'm going to go to the fourth and final example, coordinated machine learning across edge and cloud. Now, in everything I talked about, there are a lot of different research problems, but this area in particular has a large amount of research problems. So let's ask the question, how can we fundamentally improve the performance of network applications? When you think about that, some of the attributes that come to mind are the following. We want to enable massive scaling. We want to support IoT apps with high bandwidth sensors. We want to support low latency applications. We want to enhance security, preserve privacy. Okay? These are typical metrics, typical attributes. Now, some of you may say, we're already doing a good job at that because the internet works pretty well. I would say that what we're using today are those applications that the internet is good enough for those applications. But there are many other applications which we haven't even used yet because this is not good enough. As an example, I'll talk a little bit about video and video analytics because this is something I've worked on for many years and I'm very passionate about. As you know, there have been massive advances in video sensors as well as in deep learning to analyze this data and detect all kinds of things. And here you see a variety of video sensors. You see things like 4K, 8K video. You see infrared sensing. You see high dynamic range video. You see optical flow-based, motion-based video capture. You see depth views, hyperspectral imaging. You know, these are really massive advances in the type of sensing capabilities we have. And this provides capabilities far beyond what the human eye can see. So in principle, a computer who has access to this data can understand an environment much better than a human can, right? That's awesome. So this will open up many applications. The problem is, though, this is a huge amount of data. So even if we compress it, you can't get it to the cloud to do the machine learning. And to make that point even more clear, in a building like this, you probably don't have one of these sensors. You may have 10, 20, 100 of them. And assuming they're all compressed, that's still too much data to send to the cloud. So I described this to help motivate why we need to improve what we're doing across the edge and the cloud. So let's look today at how we do cloud-based machine learning. So today we have some data, and we usually send it to the cloud, and we perform these two key operations, the learning or the training of the data, and second, the inference, or I'll call it execution. I call it execution because I wanted a term that's a little bit broader than inference. So we have these two steps, the learning and the execution. Well, the problem with today's approach is that we could have issues with bandwidth. For instance, we don't have enough bandwidth to send all the data to the cloud, or it's too expensive to do that. We have issues with latency to the cloud, and also issues with privacy. By privacy, when I send my data to the cloud, where exactly is it? In what country? Who has access to it? Has it been compromised? Do other people have access to it? If I delete it, is it gone, or is it still there somewhere? These are some of the various privacy questions. Okay, let's see how we can improve on this. Well, first of all, we can do some of the work at the edge. We can do the execution at the edge and still keep the training in the cloud. This can reduce the bandwidth. It can also improve scale and lower latency, but it still has a privacy issue. Okay? Well, we can do both the execution and the learning at the edge. Great. That achieves the prior benefits, and it also provides privacy-preserving learning. But the issue is that we don't have one edge. We actually may have 1,000 or 1,000,000 edges. And how can you do the learning then across all of these edges to get the performance? So how can you aggregate the learning across these multiple edges? This is the fundamental question. So if I try to refine the problem statement, it looks kind of like this. How can we achieve these two kind of conflicting goals? We want the training performance of cloud-based machine learning, where we get everything together in a single location to do the global optimization, while getting the benefit of edge-based machine learning, where we have benefits in terms of reduced bandwidth, improved scale, and lower latency, and privacy. Okay? So these are the two things we're trying to get. Now, this is an open problem. There are many really good PhD theses here. If you'd like to work on them, you'd like to work jointly, let me know. Very happy to talk with you about these. And what I'm going to do next is just quickly describe two examples of work in these areas. Neither one of them solves the problem, but they both provide important steps. The first one's going to help to dramatically reduce the amount of bandwidth you need, but it's not going to help in terms of privacy. The second one will help in terms of privacy, but it's not going to reduce the amount of bandwidth we need. Okay? But they show you two example steps forward. Okay, let's look at the first one. So the issue here is how can we reduce the amount of bandwidth required? Well, if you think the real issue here is that we have to take all of the original data and send it to the cloud to do the training, and you realize, well, all this data is not of equal value. Some data is more valuable for training than others. If you can figure that out and only send the valuable data to the cloud, that can dramatically reduce the amount of data you have to send in the cloud. Okay? Here, so that's the basic intuition here. And this system works in the following way. First, we make some initial global model for the training. We then send it to the edge. And then we use this model at the edge to analyze some local labeled samples. If this model does a good job in terms of does an accurate job in terms of classifying these samples, then in some ways the model already does good for these samples. So it's of less importance to send those samples to the cloud. On the other hand, if the model fails for these samples, then these samples are especially important. They contain new information, and we want to send them to the cloud. Okay? So conceptually, this is a very simple way to figure out what subset of samples you want to intelligently select and send it to the cloud. And there's a lot of detail in terms of how you do this right, and this is an example paper on this. So some of the key features here is that it does reduce the bandwidth significantly, and it allows you to continuous learn and a continuous update of the models, but it does not improve privacy. Now what I want to show you is a second example, and in this example here, what we're going to do is going to show you an attempt to improve the privacy. So the privacy issue is, once again, the following. We prefer not to send our data to the cloud, because then all these privacy concerns can come up. So the idea comes up, can we take our original labeled data, and can we then make some synthetic labeled samples which capture the key features of the original data so that we can use it for machine learning, but don't actually convey any of the private information? Okay? And to do that, the idea is, can we make a local generative model that will take these original labeled samples and create the synthetic samples that then could be used in the cloud for the training? Key questions here is learnability. How well does this actually learn? Also privacy. Do these synthetic samples actually leak information about the original data, or do they actually preserve the privacy? Okay? And once again, this example shows improvement in privacy, but it does not reduce the bandwidth requirement. Okay? So the next few slides, I'm going to show you a concrete example of this. This is from the ICIP paper here from last year. And in this example, we try to make a machine learning algorithm to detect in human faces if they're smiling or not smiling, and if they're young or old. So it's a smile detector and an age detector. Just 2 bits of info. Okay? And the reason I like this example is by having human faces, it's easy for everybody to understand why we care about privacy here. So here are, for example, some faces. This top one is a smiling, young, a non-smiling, young, smiling, older. Okay? So these are the original labeled data. We then use a GAN, a generative adversarial network, to basically, where we have a generator and a discriminator that compete with each other in order to try to make a better GAN, a better generator. Once we have this generator, we give it some random data, and it generates some synthetic label data, as you see in the bottom here. So in the bottom here, you see some other faces. These are synthetic faces, and they're labeled. Non-smiling, old, smiling, young, non-smiling, old. And these faces, this synthetic data is now used in the cloud to generate the model. So 2 questions come up here. First of all, is this synthetic faces as good as the original data for building a model? Turns out in the experiments we've done, it's within 2% of, using synthetic data provides an accuracy within 2% of using the original data. Okay, so that's good in this case. The bigger question, the harder question, is in terms of privacy. Do these synthetic samples here actually leak information about any of these original images here, such that by looking at these synthetic samples, you can guess who was in the original picture? Okay? So that's what we wanted to look at. And so then we looked at how can we measure privacy preservation. One of the things, we looked at a number of examples in this context. One aspect of it is actually looking at the faces and see if the synthetic faces, as you see in this column, how they compare versus any of the original training data. So what we did here is for each synthetic face, we found the best match in training data, and they're all in the same row. So this face has these are the 5 best match in training data, and you see this for a number of synthetic faces. Unfortunately, what happens as you look across them, you can see they're all human faces and stuff, but there isn't a good match. So this suggests that this approach is preserving privacy. That is, that it protects the user identity by using these synthetic images. Now, there are a few caveats I want to mention here. The performance of these type of approaches where we create synthetic images or synthetic data to use for the learning, well, the learning performance depends a lot on the specific task you're trying to accomplish. This was a relatively simple task, 2 bits of info. Okay? Depends on the type of task you want to do as well as the data set you have. Another thing I want to mention is, in this paper we went far beyond this example. We used differential privacy and so forth to compare whether or not this approach really preserves privacy. But still there's much more work to be done. Privacy is a very big, important topic for society. And we as a community need to do more in terms of generating formal definitions and tools for analyzing if things are privacy preserving or not. I covered a lot of topics in this 4th example, so here I just wanted to show you some references. You can go and look for additional information if you wish. This is the paper mentioned on intelligent sample selection. This is the paper on privacy preservation, and here's some of the other prior work on GANs and so forth that we built upon. And also Google's doing some very interesting work in federated learning, which also, once again, tries to optimize across the edge and the cloud and preserve privacy and reduce bandwidth. Okay. So with that, I'd like to summarize. I think it's a very exciting time to work in networking and network applications. There are lots and lots of opportunities to apply machine learning in this space and to help society in many different ways. I went over 4 different examples here in the talk. And finally, if you're interested in these areas, we are hiring both interns and full-time employees. So if you're interested, come and talk with me. My email address is also there. Thank you very much.
Okay, so we have time for a few questions. So excuse me for my voice. Any questions for the other? For the malware detection while still being encrypted, can't the attacker mimic the traffic flow of the, for instance, Google search and put dummy data inside while getting data out of the
Exactly. So what happens is for detecting devices on the network, that problem there, those devices are kind of neutral. They're not adversaries. But with attackers who are doing malware, they are adversaries. So they try to continuously adapt what they do to cause havoc. And they, among other, so we publish our results here, and we provide the software available, so forth, so that the broader community can use it, and we can all learn and do even better defenses. But similarly, the attackers try to find out how they can do a better job attacking these schemes. So it's a continuous cat and mouse game here. You're exactly right.
It's that same system. Is it also fair to say like there's other approaches for kind of this deep packet inspection, like blind box? You're familiar with that work? Where it sounds like your system you can kind of only tell after the fact, right? After you've seen this pattern in the traffic. So is it impossible to kind of intercept something as it's happening?
Let's see. There are a few angles of what you're talking about. One thing I should mention is there are attacks which have occurred before. If they occurred anywhere in the world before on, let's say, a customer who has our gear, we see that information, we gather it, we bring it back, and we share it with everybody. And that's kind of a known attack. So once it happens once, we can help warn everybody about it and help stop it. That's an example of a known attack. There's also zero-day attacks. That is when an attack first comes out that we've never seen before. In that case, those will not be picked up with this. What we do there is we use various baseline and anomaly detection and so forth to try to detect things that are different. And there's some types of things that you can detect very easily and others that's much harder. For example, if this light bulb is communicating to the internet, that light bulb should not be communicating to the internet, so you know something's up. What happens is we use knowledge about how the various devices, what the devices are, what the applications are, what the users, how should they be behaving, and if they behave differently from that, that suggests that there could be issues, and then you have to look more closely. But it's, especially for zero-day attacks, it's really, really hard. That's where things like segmentation is very important, because you may not be able to stop the attack because you've never seen it before, but you can limit its impact because it can only go so far. Does that make sense? It's a continuous cat and mouse game in terms of security. Yeah. RSA conference was just held recently in San Francisco, and there's a lot of great talks and stuff online if you're interested in this area.
I was actually just going to ask about the RSA conference, since you mentioned that you attended. What are you most excited about that you saw there as far as promising next steps in the future?
Let's see. Well, one of the things that I like is that with this intent-based networking, where we have this feedback loop, We haven't had that feedback loop before, not at short time scales. It's always been a long time scale. It's always been humans in the loop with a long time scale. Now that we have this very fast feedback loop and we have a lot of machine learning. So for example, in modern switches, routers, APs, we have x86s there. And we can have containerized applications running there to look for threats and other things. So every network element can actually be a sensor now looking for threats and looking for anomalous behavior. And once you identify that, you can send that information to the controller, and based on the type of threat it is and the repercussions of doing, you could either do A, B, and C, and for each of these there'll be different implications on your production network and so forth. You can help decide what's the best thing to do. So the fact that we have much greater visibility in terms of what's happening, both the regular operation of the network as well as threats, and then the ability to quickly react and make changes and stop attacks, that's incredibly powerful. And that's going to change the game in many ways for a variety of things, not only to reduce attacks, but also to improve the performance of networks. For instance, here at Stanford, you have, especially some of the big classes, you may have hundreds of students in a single classroom. They all walk out the classroom at the same time, and they want wireless connectivity to the next thing and so forth, right? You have these massive changes that are occurring, and you want the network to adapt quickly. In the past, it was relatively hard to get networks to adapt like that. Now we can do it very, very easily. And especially in the future when you use augmented reality, virtual reality, and other sorts of applications like that.
Very often when you talk about things like anonymization and differential privacy, it seems like there is some sort of trade-off that you have to make between model performance versus privacy guarantees. How do you think of this? Like, how do you decide what's where to draw the line?
That depends a lot on the use case, and that's, as I mentioned, there's a lot of work I think we need to do as a community in terms of figuring out what are the right things to do in different situations. And there's not a single answer that solves everything. Yeah, but it's an awesome, it's a very good question, and it's an awesome area, I think, also to do research in.
I have a question as well. You mentioned GANs in your talk, and I imagine some of these applications have different flavors of ML that you're using. Can you give us a sense of what are the latest trends in what you're looking at? Is reinforcement learning, an important item? Is it?
We use kind of everything.
Important?
Oh yeah, so explainability, interpretability, so forth is very important. The reason it's very important for us is that you want to be able, so in different cases, different scenarios, the reason it's important is different. For us, in many cases, for instance, the nuclear power plants which are run by this, right? You want to be able to understand any action that will be taken and why. You understand reliability, predictability, all of these things are really crucial. So understanding what happens is very important. Note that there are other applications where you don't necessarily need to understand why various decisions are made, but you want other attributes. And detecting objects in an image, you may not need to know why it works sometimes. As long as it does it accurately, that may be okay. So depending on the use case of it, you need different things. Also to your question about what types of machine learning is used, we use basically all of them, because for different problems you need different ones. And also even for like a single problem like security, we often bring together different sorts of models, and then we pool the information in different ways to try to get the right estimate. So bringing multiple of these together is kind of key for achieving high performance, reliability, and so forth.
Okay, any more questions? Let's thank John again.
Thank you.